Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. So where are we? Today, we are going to continue and finish the white column stores lecture. Actually, it's as you can see right here in the lecture hall, it's only a couple of slides left. And then we'll move on to data modeling, which is the last part about storage. And then we'll start querying data next week. It seems that the network is going again. It seems that it was broken just an hour ago. Then I called the IT help desk, and then it just worked exactly when I wanted to show them that it doesn't work. So this is great. So now I'm just crossing my fingers that that the network will stay with us, and otherwise I just switch to Wi-Fi like last time. All right. So let's get started. So. You remember the logical model of HBase, right? Where we have these row IDs and these column families. And when you take the intersection of a row ID and a column family, you get what we call a store or an H store, which is the granularity of storage for HBase, right? So this is what we saw. And we were solving at the end of the lecture last Wednesday. We had the problem that within an H file, remember that an H file is the file that we store physically on HDFS. In an H file, we sort the key values in ascending order, right? So there is an order. It's always sorted in ascending order. I think one of the names of the H file format, I think at Google, is also known as an SS table. Who heard of SS tables? Nobody. Okay, it's one other way that it's called. It's basically sorted strings in there. So everything is sorted, but it seems to be in contradiction with something else that I told you, is that in HBase you can randomly update cells. You can modify the value of a cell. You can add new cells and so on. So that seems in contradiction with the fact that it's sorted here. And in HDFS, I told you we don't have random access. So in HDFS, I don't have any way to modify in place and add key values in the middle of the H file. So this seems to be a problem, because how can I update anything? And so I started to explaining to you the solution. And the idea is that we never modify H files or anything. We just write full H files, always write an entire H file. And the modifications we always do in memory, and then we regularly flush them, as you might remember. So remember this hierarchy that we have here, where a region, a table is split horizontally in regions, assigned to region servers. Then the regions are split according to column families, and every column family gives you a store. That's the granularity of storage. Physically on HDFS, we have H files that are HDFS files, right? And these H files are themselves cut into H blocks, but these H blocks are only here in order to facilitate the lookup of key values within an H file. Has nothing to do with HDFS blocks, right? So we just have these blocks within the H file, and the H file contains an index that fast tracks you directly to the place that the key values you're looking for are stored, right? So these are I call them H blocks to distinguish them from HDFS blocks, because I don't want you to confuse them. So what are the differences? An HDFS block is always exactly 128 megabytes, and then you cut. That's it. It's really, you cut exactly at that position, except for the last one that can be a bit less, right? But in HBase, we saw that the H blocks are 64 kilobytes, but it's not 64 kilobytes strict. You don't actually cut exactly there, because what you don't want is to cut in the middle of a key value. That you don't want. So what you do is that you put your key values in an H block until you have 64 kilobytes, but then you add to finish the last key value, right? So it's going to be more than 64 kilobytes. You just put whatever is left to complete the final key value, and that's it. It does mean, of course, if your key value is 10 megabytes, which I told you can happen, then your H block might actually grow as much as 10 megabytes, right? But it's totally okay. But again, the only goal of the H blocks is to index the H file in order for you to very quickly find the key values that you're looking for. And in fact, when I'm talking to you about all of that, I couldn't care less about HDFS blocks. HDFS is just some file system that we are using, and we don't care about the HDFS blocks, just like when you use your disk and store some spreadsheet files, you don't care about the 4 kilobyte blocks on your hard drive, right? So here is the same way. HBase is a client of HDFS, and we use HDFS to write files to it, and all of these H files are HDFS files. All right, so I hope that this helps. And of course, in the H blocks, we have key values, right? So now, what happens if I want to read the data? Where do I read it from? If I have, let's say, a user request, they are asking for a specific interval of row IDs, for example, and for a specific column family. So I'm basically looking for the key values in order to be able to answer to the user, right? I want to give the data to the user. So where do I look? The answer is actually quite simple. I look everywhere, everywhere. I look every single H file on the HDFS, and in memory in what I call the mem store, everywhere. So it means that I got them maybe from here, from this H file, from this H file, from the mem store, and so on, and I gather all of the key values that I want. If they want the latest version, then I might trim the earlier versions if I have newer versions, and that's pretty much it. And then HDFS, so me, I'm HBase, I am HBase kind of now. And so I take these key values and then I present with this, I can present the results to the user, the actual data that they were looking for. For whom is that clear? Okay, the fact that I look everywhere is clear, right? Right, because this is the older data that I have flushed. Remember that we flushed the H files when the memory was full. And this is the recent data. That's what I very recently wrote into memory, and that's older. For whom is that clear? More raise hands? Awesome, perfect, you're following. Okay, now you might have been wondering, how come that I can have multiple H files on HDFS? Because I told you might have multiple H files for the same store. It's very simple because we keep flushing them. Every time the memory is full, I just flush the key values that were in memory in sorted order, and I create a new H file. So if I do it twice, 3 times, 4 times, 5 times, 10 times, I'm going to end up with a lot of H files, right? After a while, maybe 1,000 H files. Now, can you imagine having to look at 1,000 H files at every request? It's just, that doesn't make sense, right? It doesn't scale. At some point, you have so many H files that we cannot handle them anymore. So it's just not viable to just keep flushing a new H file every time the memory is complete. I have to find something else to make it a bit more efficient. That something else is called compaction. And the idea of compaction is that once I have a certain number of H files or multiple H files in there, like for example, here I flushed the memory 3 times and that got me 3 H files, what I can do is compact them to a single H file. So I will take these 3 H files and merge them, compact them to a single H file that of course is going to be the total size, the sum of these 3 sizes, right? What do you think is the complexity for compacting these 3 H files to an H file? What is the complexity of that? So who thinks it's exponential? Who thinks it's polynomial, but like quadratic or cubic or something? Okay, who thinks it's n log n? We have a few answers. Who thinks it's linear? Ah, that's where the majority is. Who thinks it's logarithmic? Okay, who thinks it's O of 1? Okay. Well, the answer is that it's linear. And let me give you a bit feedback on the answers. The reason it cannot be logarithmic is that you might remember that one of the principles of complexity theory for algorithms is that the complexity cannot be less than the size of the output. Right? So the size of the outputs, what we want to write back, is linear. So there is absolutely no way you get better than that because you need to write every key value. So it's at most linear, at least linear. But now you might wonder, why not n log n? Why did you say n log n? Who said it because of sorting? Yes, some of you. So that's clever. You need to sort the key value pairs. So you might think in order to sort them, we need n log n, right? But the thing is, we don't exactly need to sort them, or at least not to sort them again, because you might remember that here it's already sorted. here, it's already sorted here, and it's already sorted here. So in fact, it's not like we are starting from scratch. We are in fact merging several sorted lists. And I consider that the number of HFiles is a constant, right? It's so in order to merge them, I need linear time. In fact, who remembers merge sort? Right? Merge sort means you sort subsets of the inputs, and then you merge the intermediate input, intermediate output that is already sorted. Overall, it's n log n, but in that case, we only do the second part of merge sort. We already had our pre-sorted HFiles that we take it from, and all we need to do is merge them. In other words, what we need to do in order to produce that output HFile is just a parallel traversal, a concurrent traversal of these HFiles, and we just traverse them concurrently and always keep outputting the lowest key value we find with pointers that just advance into the files, right? If you took information retrieval, you probably remember that we were actually doing that with standard inverted indices, right? To compute the union of postings list. Who remembers this? Who attended information retrieval? Okay, who remembers that we computed the union and the intersection of postings lists in order to execute AND and or Boolean queries? Oh, some of you, okay, awesome. So I hope you didn't forget everything as soon as the exam was gone, right? But anyway, we basically traverse each one of these HFiles. So I have a pointer here, a pointer here, a pointer here, and I traverse advancing the pointers concurrently, and I keep writing the output in ascending order of keys. This is called compaction. So I take them, and what I get is all of these key values, but now it's a single bigger HFile on HDFS. And of course, there will be a single index in that HFile that indexes my key values based on H blocks. So it's going to be faster to look up key values in that one than it was to have to look up in 3 different indices and 3 different files, right? Okay, so this is compaction. So in summary, what I did is I flushed the key values to disk when the memory was full, starting fresh with an empty memory. And when I had too many HFiles, I compacted them. So you see that I keep pushing the data to the disk, and I keep compacting to larger HFiles. And in fact, there is a name for this. It turns out there's a fancy name. So if you want to, look great in front of your friends at the next party, then you can just talk about this log structured merge trees, sorry, LSM trees, log structured merge trees. This is what you have on the right. LSM trees are absolutely fundamental in big data. In fact, you will see them everywhere, not just in HBase, but in plenty of other places, even in MapReduce on the physical level. So I will need to put it in perspective with something else that you might remember from your relational database lecture, which are B plus trees, B trees and B plus trees. Who remembers B trees and B plus trees? Okay, so this is one of the ways to index your data in a relational database in a way that has some order in it. You might remember that when we introduced the B plus trees in relational database management system, the main reason was we wanted to avoid the latency every time you have to read. You want to read in blocks, right? So the idea of the B plus trees is that they are seek time bound, right? When you access them, you basically have some latency every time you want to access a value, right? That actually comes from the fact that in a relational database management system, it's OLTP, so you might have access to small portions of the data every time, right? Not aggregations over the entire data set. So this is the reason why we use the B plus trees. It's seek time bound, but we managed to get a small improvement by putting them as blocks on the disk so that we only read what we need. But here we have something different. We have a different problem. We have the problem that we need to write entire HFiles every time because it needs to be sorted. The only thing we can do is write an entire HFile. There's no way we can random access writes to it. So our problem here is more the transfer time. It's basically going to we want it to be to be bound by the transfer time and not by the latency, because the goal in big data, just to give you the intuition, we just want data to flow around. We don't want data to stop flowing around because you're waiting for something. We just want data to flow. So this is why we designed the LSM trees, and I will connect that to batch processing, because in fact, that is the batch processing I have been telling you about. But I think the best way that I will explain LSM trees to you is with an animation, because I think when you see it, you will get it. When you see it, you will understand how they actually work. First, a brief high-level explanation. The idea is that you have what is in memory. That's the very, very fresh data that you just created. Then when you flush, you create a first level of HFiles. Then when you compact HFiles, you get larger, fewer HFiles, and then you can compact, and you keep getting larger and larger HFiles. So the idea is to have all of these structures at all these levels together, and this is actually optimal in a logarithmic way, as you will see. All right, but again, the best way is the little animation, and I hope that with this animation, you will just get it. You will have hopefully aha moments. So let me explain log structures merge tree. You see it written, right? Log structures merged trees. So I'm starting with an empty system, and I keep adding key values, and then at some point, my memory is full. What do? You flush, exactly, you flush. So what do you get when you flush? You get some HFile in there because of flushing, and the memory is now empty. So the HBase continues to have its life. So you keep adding key values, right, into the system, and then the memory is full again. So you flush, exactly. So what you get is a second HFile. So now, for simplicity, I'm taking the number 2, right? In reality, it doesn't have to be 2, but I'm taking the number 2. If I have 2 HFiles, this is what's going to trigger compaction. I don't want to see 2 HFiles like this of the same size. So I compact, exactly. We're going to flush again, don't worry. Now it's a compaction. So what we get is, when we compact or merge them, we get an HFile that is twice as large, but now there's only 1. Okay, so then we continue to use the system, and then the memory is full again. So now you can see it, we flush, exactly. So now we have an HFile there. And that's fine, right? Now I have this larger HFile, and I have this HFile there. I'm fine with that. The memory is full again, so I flush, and there's 2 HFiles, so I compact. Perfect, you're good. You see, you're following. And now I have 2 HFiles that again have the same size, so I compact them. Exactly. So now what I get is again a single HFile, but it's going to have double the size. You see where this is going? Yes? HFiles which are the same size? Yes. In this algorithm, in the log structured merge tree, yes. Yeah, that's exactly what's going on. And now I continue. You see the memory is full, so I flush. Then the memory is full again, so I flush. 2 HFiles with the same size, so I compact. The memory is full again, so I flush. The memory is full again, so I flush. Then so you see the idea, right? Who saw that we were actually counting in base 2? Who saw this? Some of you. Let me come backward and you will see it. I just need to put myself at some position that you can see, right? Okay. So this is 0. Look at it, base 2, but reversed, right? So this is the first digits and you go left to right. So this is 1. This is 1, 0, so 2. This is 3, 1, 1. This is 4, 1, 0, 0. This is 5, 1, 0, 1. Who sees it? Right? We're just counting in base 2. That's what's going on. Of course, here I do it in base 2 because that's better for my slides, but in practice, you don't have to do it in base 2. You can do it with more HFiles, right? But this is the idea. Who gets log structured merge trees, right? It's really this idea that you keep flushing, but at the same time, you also compact, but it's logarithmic, right? Because we are counting in base 2 in this way. So the idea, actually, of what's going on is that the freshest data is in memory, then the less fresh data, but still relatively fresh, is in there. And the more you go there, the more you get older and older and older data, right? And if you dig maybe long enough, and maybe you will find HFiles that were created millions of years ago, and maybe you have dinosaur fossils in there, right? Because it's actually so old. So this is really the idea, super new, super old, okay? So this is log structured merge trees. And again, they solve the problem that you cannot update in place because you don't have random access. The only thing you can do is write entire HFiles. And so this idea of flushing and compacting is exactly how you manage to keep something dynamic for the user. They keep creating key values, but you just keep flushing and compacting them to larger and larger files, which means that when you're interacting with HDFS, you actually just write entire files. Do we have a question? Yes. Small hops. Yeah, all right. Small hops, just small hops. Yeah, 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 thank you.
So is it in the compact, if you want to update a value, like you want to use the same key but update the value, is it in the compact step that you pick the newer value or something? Or when does the update happen, or how does it happen?
Yes, so this is part of the solution you're actually already optimizing by saying that you do it by compaction. So let me give you the first half and then show why you are also right. The idea when you update a value is that you create a new version of that value. It's just like when you use Git to put your code in there and you commit code, you're not erasing the older code, you're just adding a new version. It's the same thing here. When you update a value, you just create a new version of that value. And it means that you will still have the older version somewhere at some level in an H file. But since you read from everywhere, when you read, you will both see this older version coming from an H file and the recent version coming from memory. And so if the user wants to see the latest version, you just drop for every cell, you drop the older versions and only keep the latest one. Does that make sense? That's one half of the answer. The other half of the answer is, what if you keep accumulating versions and versions and versions? Then you might want at some point to also drop them from the physical system, right? Maybe you don't want to do that. Maybe you want to keep everything, but maybe you want to drop the older ones when they are, let's say, 5 years old, or I don't know. What better moment to do that than when compacting, right? It's just like you compact the H files and you notice, oh, while I'm compacting, I notice this is an older one. Let me just use the compaction moment to just drop it. And then when you write the compacted H file, you will just omit it, and then you will have deleted it. This is how deletion works. And in fact, if you don't want to update a value, but delete a value, you just create a new version of that cell saying that it's empty. In fact, that was that last bit in the key that I told you about, right? It's basically a tombstone. It's a way to mark it as deleted. And so if you see that there's older values, but the most recent one is marked as deleted, you just output it as non-existent to the user. And of course, the next time you compact, or after a while, you will at some point drop the older value because it's too old, okay? That's the general idea and how log structured merge trees allow you to do that, okay? Yes?
Yeah, thank you.
Yeah, there's another question over there.
What happens when you reach the limit of the H file size?
Oh, but in HDFS, there's no limit, right?
Oh.
You can actually go very, very large in HDFS.
Oh, okay, okay.
Yeah. So basically, I would imagine that in the system working normally, you will not easily reach a point at which it's very large. But even if you do, let me talk about what if you do. What if at some point you reach a size that slows down the whole system because it's too big? Then you might remember that I told you that when a region grows too big, you can split it, right? So you can say now my region has so many rows in there that I'm going to split it in two. So I marked it as split. And then all I need to do is take my H files and split them, right? But this is linear, right? You agree? You just need to traverse the H file and just output left and right what you need, right? And even since it's sorted by rows, you don't even need to do it. You just take the first half, put it in there, take the second half, put it at some other place, and you got your two H files. Does that make sense? All right, and then you split, and then at a later time, it might be that the region is, one of the regions is transferred to another server. All right, another question? I saw another raised hand. Small hops, yeah. Yeah. Yeah, we are just growing more careful and more careful with time with this Yeah. All right.
You said we perform deletions by basically every time we compact, we just remove the file or mention of that file. But for deeper files in the LSM tree, I mean, you're much less likely to maybe get to that point of compaction where you would actually touch that, which means older files are much less likely to get deleted. You know, is there a process for that where you go through again and clean up or something?
Yes, so that is kind of related to the former question in that sense that when it starts to be so deep, because that with the dinosaur was a joke, right? You don't keep them for thousands of years. But the idea is that at some point when it starts to be the case that they are growing so large that you will very rarely access them, this is when you can split the region, right? Then you split the region and then you're back to something more reasonable.
Okay, sorry.
Right?
Maybe I just didn't get that. Thank you.
Thank you. All right, so let me continue. So what I've just described is basically batch processing. We've just seen batch processing in the sense that the batches are the HFiles, right? It's just sorted lists of key values. We don't manipulate them one by one, except in memory, we just batch process. What I wanted, the reason for the title here, that there's also this when not to use the cache, it's the idea that the data that is in the HFiles, that is normally not in memory, you can still have an extra cache in memory, but this is not the same thing as the mem store. The mem store is really the data that has not been persisted yet to HDFS, but you can have another structure, a cache, that holds the key values that are normally in the HFiles on HDFS, but that were recently accessed, right? So you can keep them, and that way it accelerates the process of querying. So there are a few optimizations. But there are cases in which caching will not help, and especially if you are really scanning through the entire collection from the start to the end, then the cache will not help you very much, right? Because you keep accessing other key values. And another pattern where not to use the cache is the random access. You just randomly access key values, but it's all over the place, so you never get a chance to hit the cache, right? It's always a cache miss. All right. But actually, I wanted to, I made it more lightweight this year. I removed a few slides regarding the cache because I really want to keep it very high level. So that's the first optimization, that you can keep some of the key values normally on this, you can keep them in memory. There is a second optimization that is actually wonderful. It's called the Bloom filter. Who heard of them? So the Bloom filter is a way to not have to read all the HFiles, right? Imagine that there are 10 HFiles on disk, but you have information from a secret source that the key values you're looking for are surely not in this HFile and this HFile and this HFile. So it means you don't need to read from these HFiles, you will only read from the other 7 HFiles. So if you can save yourself the trouble of reading some HFiles, you make your system faster. Now, what is that secret source that tells you the key values are surely not in that HFiles? This is the Bloom filter. The Bloom filter is some technique that you will see in the exercises that is able to tell you, if you ask it, it's like an oracle. So you come to the Bloom filter and you say, dear Bloom filter, I'm looking for these key values. Are there in these HFiles, right? And then the Bloom filter is going to either answer you, no, the key values are surely not in that HFile, or it's going to answer you, maybe they are. Maybe they are not, maybe they are. In that case, you read the HFile. So in one way, it's a certain answer. It's certainly not in the HFile, but the other way, it's a maybe, right? It's either a no or a maybe. You just don't get a yes.
We have a question on
Yes?
Zoom. What happens with the H files when a region is split? When we potentially have H files of different sizes, which then affect a future merge?
So when we split the region, we just split the HFiles as well, right? So you have the first half of an HFile that becomes an HFile of the first region, and the other one becomes an HFile of the second region. But then you separate them, and then there's the store border between them, and they are no longer handled together. Was it your question? Yes, let's assume yes. All right. So in that case, for example, I have all of these HFiles, but this Bloom filter oracle told me that the three that are marked in gray, they surely don't have the key value, so I don't need to read from there. This is a fundamental principle in big data. If you have a way of knowing that the data you're looking for is surely not at some place, then you don't have to read it. And since you remember that the big bottleneck we have with big data is reading I/O, right? It's the disk I/O. Anything we don't need to read is a good thing, right? So this is why the Bloom filters are actually super useful. Internally, I'm not going to tell you details. You will see it in the exercises, but it's based on hashes, right? You can just use some hashes, and that can tell you if yes or not the hash of the key value is in the H file, right? But it's more complex than just a hash, as you will see. It involves several of them. All right, so this is the Bloom filter. So that's what I told you, that the key is not contained in the file. All right. So random access, no, that was actually coming back. Yeah. So now, in order to bootstrap the whole thing, when you read with HBase, how do you know which region server you have to deal with, right? If you're a query and you want an answer. The idea is that in addition to all the tables you might have in HBase, there is a table called the meta table that is special because that table stores the information regarding the regions. This is the table that tells you these are the regions and this is the region server responsible for it and so on. It also contains the regions that are marked for splitting. This is also where the region splits are stored when you do them and so on, right? So it has a lot of information in there that I will not bore you with, but the idea is that there is this meta table, and this is actually how everybody knows where to find the regions on the cluster. It used to be that there were multiple levels of meta tables in older versions, but they simplified the things a little bit, so now there's just the meta table. But you could also imagine some more logarithmic thing with all kinds of levels of tables that's until you get to the regular tables. All right, so the idea is that when you have a query like this, you just, the client just connects to the HMaster, right? And then looks where is my meta table. Then it asks the meta table, okay, here's the data I'm looking for. Where's the region? And then it can connect to the appropriate region server. All right. So a few final words. HBase is implemented in Java, just like HDFS. It also has a REST API, right? Like any good system has a REST API. You remember what a REST API is for, right? It allows you to access it from any programming language that has an HTTP library, even if that language doesn't have an implementation of HBase, right? That's what the REST APIs gives you. They facilitate the use of a server in many programming languages. All you need to do is the HTTP library. All right. Now I'm coming back to some question that was asked about data locality and how, because I told you HBase is a client of HDFS, so we treat HDFS as some outside system, but in practice, they are not quite distinct because they are running on the same machines. The region servers run on the same machines as the data nodes, the HMaster on the same machines as the name nodes. So how do they work together? Well, now put yourself in the situation that we've just flushed the data to HDFS. You remember that when a client writes to HDFS, there is a replica of the block stored locally, right? Now, who is the client of HDFS? Is the region server that's flushing, right? So the region server flushing wants to write a file to HDFS. So every block of the H file that is being created will have a replica on the same machine as the region server. So now you have locality because there is a copy of every block on the same machine as the region server. Who understands that? Right? And this is because the region server is the client at the moment that it flushes the data. So we will have replicas at other places, of course, so that when it crashes, there's no problem. But we have a copy of the block here, and that allows us to short circuit. It means that when you want to read the data, the region server, if it knows that there's still a copy of the block in there, it doesn't need to go all the way and apply the entire HDFS protocol. It can just read it as a local file, all of the HDFS blocks of the H file, right? So this is called short circuiting. It's kind of cheating because it's the same engineers that designed the two, HDFS and HBase, but it actually works. The problem is that you know that HDFS has a life, and you know the the HDFS blocks, they tend to travel around. And so after a while, you might no longer have all of the blocks with a replica on the same server, and you lose that locality, right? I feel like I'm giving a quantum physics lecture because it feels like the wave function, but anyway. So the idea is that you don't have the blocks anywhere anymore at the same place. So now that's less and less efficient. But guess what? We will compact at some point, right? We flush and we compact. So what happens at the next compaction? We create a new H file. And when we create that new H file, we again have all of the blocks with a copy on the region server. Every time you flush, every time you compact, you bring back a copy of all the blocks on the same server. This is why the locality is so important here. For whom does that make sense? Right? And now you probably start to connect what we did on HDFS, what we did on HBase, and the way that they interact. So now I wanted to move on to something very, very quickly, just to amaze you and show you how beautiful the technology is becoming with the successor of HBase. So what's even newer than HBase, because it was already quite a few years ago. Maybe I'd start with saying that HDFS, so GFS, the Google File System, is also not the newest. And now there is another system that I think is called Colossus that has superseded it. It might be they have an even newer thing because I have no idea what's happening there. So maybe that's not even the latest anymore. But they already have newer versions, newer systems after HDFS. So Colossus is basically replacing a GFS or HDFS. And HBase or Big Table, which is the original name, is superseded by something called Spanner. So let me just show you how what you have learned is useful to understand this as well. Because what's actually happening is that we still have this idea of column families, columns, rows, and so on. They generalize the row ID to several columns. Doesn't have to be only one. Just Cassandra does the same, actually. So now you have multi-column primary keys, multi-column row IDs. And instead of regions, they have tablets. So the difference with a region is that a region is a contiguous interval, but a tablet is made of several intervals, right? So it's slightly more flexible. That is the first difference. And the idea is that now we can have, there's so many zeros that I have to think because before I say that, it's a trillions of rows. So you can have trillions of rows in there as opposed to billions of rows in Big Table or HBase. So now if you want to fit trillions of rows, you might realize that a data center is probably not enough. So you need multiple data centers, one in Frankfurt, one in New York, well, you know, in plenty of different places. And so now what you have is not only this centralized architecture, but you have all of these local, in every data center, you have this coordinator node and worker node, but now you have a universe master that controls all of the data center, right? So we added one more level, and now it's all over the world, over multiple data centers. That's what's going on. And so this is why we can now have trillions of rows. So now we scale up the data center. It's no longer that we have multiple computers that we pile on top of each other. Now we pile the data centers on top of each other, right? So it's actually quite impressive. And yeah, that's the latest developments of everything. And now we even have millions of machines on which the data can actually be stored. But the good news is that since you learned everything that we've seen so far, you can understand that without too much difficulty. All right. So that was just a short, high-level view of what happens even more recently than Big Table. But again, it reuses the ideas. We have 5 minutes until the break. Are there any questions? Yes?
I'm just thinking a little bit about compacting, and it sounds like you can do this indefinitely, right, in an HDFS context. But is that, first of all, the first question is it an atomic transaction? So what about if I want to read something and you know, part of the keys are going to be contained by this by the HFiles, which are part of the compacting transaction? So how is that going to work out?
Mm-hmm. So I will try to give a high-level answer. I'm not a specialist of transactions, but here's my understanding. the transactions, so it's basically ACID, the ACID properties that we have in the classical relational database systems. They give you guarantees that you don't need to worry about, right? For example, it's ACID is basically atomicity, that it's all or nothing. It's consistency in the sense that you know that before and after the transaction, you're in a consistent state. I is isolated, so it looks like there's no outside world. You're just the only user of the system. And D is durability, meaning that you don't lose the data that you have saved. Now, what happened in the more recent big data systems, it's too challenging to offer ACID, so this was dropped. And this is the idea of the CAP theorem, right? That we no longer offer these guarantees, at least on the first try, we don't. But now a lot of people are trying to bring them back in some way, right? So in the early systems, we just have eventual consistency, and it's not necessarily consistent. The goal, and now it's getting better and better. Actually, a lot of the more recent systems manage to bring back some of these properties to you. Now, in the very case of HBase, one of the ways to get some guarantees or to bring some sort of ACID-like property is to have linear versioning, right? You have versions. And you have version 1, version 2, version 3, and so on, and you just keep going. It facilitates the consistency because then when you create a new value, the worst that can happen is that somebody else reads an older value, but it's just the time is still elapsing, right? At some point, they will read a newer one. So the fact that we have these linear arrangements of the versions is already kind of bringing us some sort of guarantee in that sense. And so just like in HDFS, while you are writing the data, you don't guarantee that it will be seen immediately, but you guarantee that everybody else, in the worst case, just sees earlier versions of the data, right? And at some point, when you wrote it, then they will see the newer version. And the way we get this linear versioning is with the lock at the level of a row. Never you have two people writing the same row. It's always one person at a time writing a given row in there. So this is how you get this linear system. And this is to be seen in contrast with what you saw in Dynamo, where we didn't have a linear versioning system. It was a tree with the vector clocks, but then you have to deal with the conflicts, right? And then it's something that in ACID you wouldn't have. You don't want to have that in ACID, but it exposes it to you more, right? So in terms of hierarchy, really, if you have eventual consistency, you will see conflicts. You have this tree of versions like Git. Then one level higher, at the cost of locking the rows and being slightly slower, you have a linear versioning system, right? One version after the other, strictly ordered. It's not fully ACID. You still need additional levels to reach it, but this is kind of something on the way of being ACID compliant. Did I at least partially answer?
Partially, yes.
Partially? Yeah. Okay. We can also discuss more offline. I might need to do some more research because, again, you cannot be a specialist of everything nowadays, even databases. But we can continue offline, and I can dig a bit if you need any more information. Right? Okay. Thank you. All right. It's incredible, because back then, I mean, if you go back thousands of years ago, people knew everything. I mean, you have the same persons, they knew everything that there was to be known about mathematics, about physics, about philosophy, about literature, and so on. And the more the centuries elapse, the more it has become impossible. Like now, even in computer science, a computer scientist can no longer know everything. And even in databases, you can no longer know everything. So it's incredible the pace at which it's evolving. So you need a T approach, right? You try to have a broad coverage or on the high level, everything that's going on. And then you become highly specialized, especially if you want to do a PhD in something in particular. All right, we deserve the break, right? So this is the end of the white condenser lecture. And right after the break, we'll dive into data models for denormalized data. So thank you very much. And I'll see you in 15 minutes after the break.